Over Labor Day weekend, there was a lot of activity on Lake Michigan, but that lake is far from an open book. I'm your Manitowoc neighborhood reporter Preston Stover, following a find deep in the lake that could open doors to discovery.
Something strange had been stirring beneath the calm surface of Lake Michigan. At first, it looked like an oddity found by careful sonar operators and curious fishermen. Deep, perfectly circular holes showing up on the lake bed in places where nothing like that should exist. People who work with the water noticed them in routine passes and marked them for later study. Those early marks turned into a pattern. As more teams scanned the bottom, the strange shapes kept appearing. The holes were smooth and sharp-edged, not messy depressions, and they reached down into sediment layers that had not been exposed for thousands of years. The discovery pulled researchers from different fields into a single effort. Geologists, hydrologists, seismologists, and naval technicians all began to focus on the lake. Autonomous underwater vehicles, research ships, and small submersibles mapped the holes in fine detail. Scientists expected to find signs of erosion, gas release, or some human activity. Instead, they found circles cut clean into compacted sediment and stone. In several places, layers inside the openings seemed pushed upward and then pulled away, as if something had moved beneath the lake bed and left empty space behind. The walls of the holes were unusually smooth, not the ragged edges erosion would create, and their presence could not be explained by any local drilling or known construction work. What worried the experts most was the silence around the phenomenon. Normally, when the ground changes in significant ways, there are signs. Small earthquakes, tremors, or changes in water chemistry often happen. Wildlife reacts. Fish flee or die, and plants show stress. With these holes, there were none of those clear signals. Water temperature readings stayed steady. Chemical tests from water samples near the holes came back almost identical to control samples taken just a few meters away. Microbial life showed no sudden shifts. Fish swam near the openings as if nothing had changed. The absence of ecological alarm made scientists uneasy. It implied that whatever was happening might not be energetic in a way they understood, or it might proceed in a manner that left little trace at the surface. The holes were not a single local problem. Rather, they appeared in clusters spread across different parts of the lake bed. Their spacing did not match familiar patterns of erosion or underwater currents. Some clusters formed geometries that seemed deliberate, with circles arranged in lines or polygonal groupings. That patterning led researchers to take a wider view of the problem. If the holes connected or followed structural lines deep beneath the lake, the implications could broaden to include larger regions, not just isolated spots on the bottom. The research effort expanded quickly, and with it came urgency. Teams revisited archival data. Old sonar surveys, some recorded decades ago, held faint blots and signatures that previous analysts had dismissed as noise, debris, or instrument errors. With new eyes and new tools, those old signatures sometimes lined up with the locations of the recent holes. The idea formed that the phenomenon might not have started this year. Instead, it could have been a slow process for decades or longer, reaching a point now where modern equipment could clearly see it. In the western reaches of the lake, reprocessed imaging revealed a long-buried geological structure that had once been cataloged as an unremarkable igneous intrusion. New methods showed that the formation extended deeper and aligned with clusters of holes, hinting at a link between what lay beneath and what had opened above. Sonar and seismic work painted an unexpected picture of the underground. Advanced seismic tomography detected faint, tunnel-like shafts, extending from the base of some holes and threading down into the crust. These features did not match standard faults, lava tubes, or erosional channels. Some were straight and narrow, plunging down for great depths. Others branched like roots. Their material composition also seemed different from surrounding bedrock. In some respects, they looked like scars from ancient flows or pathways where fluids or hot material once moved through the crust and later cooled into unusual structures. The material sampled from the hole edges added more puzzles. Sediment cores contained layers of clay and rock that dated back to the end of the last ice age. That by itself offered a rare look into old climates. But other findings were stranger. Some mineral inclusions showed isotopic ratios suggesting exposure to extreme pressure or heat at some point in the distant past. Tiny flecks of high nickel alloys turned up in a few deeper samples. Those fragments raised questions. Were they remnants of ancient impactors, pieces of meteorites that sunk and embedded in the bed millennia ago? Or were they signs of processes not normally expected in continental interiors? Scientists proposed many hypotheses. One idea was that gas pockets trapped under the lake bed might be releasing suddenly and carving out the voids. Methane and other gases can cause submarine pockmarks where bubbles rise and sediment collapses. But consistent signs of degassing, bubble plumes, altered chemical markers, and visible disruptions were mostly missing. Another hypothesis suggested that deep water currents might scavenge sediment and leave sharp cavities. Yet the placement and symmetry of the holes poorly matched known current paths, and the tidy walls argued against rough scouring. Some researchers considered whether pockets of salt or other minerals were dissolving in place, but the geochemistry so far did not support a simple dissolution story. As the list of conventional ideas ran thin, teams broadened the search to electromagnetic and acoustic signals. When scientists sent sound waves into certain holes, the returns were odd. Echoes and standing waves behaved differently than expected. Specific frequencies seemed to ring and resonate with harmonics that suggested cavities or material contrasts at depth. Electromagnetic instruments occasionally recorded faint pulses or spikes in conductivity around some holes, readings that did not line up with solar or atmospheric activity. Those anomalies were weak and inconsistent, but they suggested that something below might be affecting local fields in ways not yet understood. The government also took notice. Agencies like Geological Surveys and Homeland Security coordinated with academic teams to track developments and consider implications. Officials stressed that the term "red alert" in internal briefings described the need for immediate scientific focus, not a call for panic. Still, contingency planning began quietly. Engineers ran models asking difficult questions. What would happen if a larger pocket collapsed? Could sections of the lakebed slump, altering water flow or shipping channels? Could underwater infrastructure, such as cables or intake pipes for cities, be exposed or damaged? The Great Lakes are a major artery for commerce, and any disruption to depth, sediment, or shoreline stability would ripple through ports and industries that rely on predictable conditions. Local communities felt the tension between concern and curiosity. Fishermen, sailors, and people living on the shores began to watch the water a bit more closely. Town halls and public meetings gave scientists a chance to explain what was known and what was not. Indigenous leaders shared stories that had been passed down for generations about strange places in the lake and openings that seemed to breathe or make odd sounds. Those oral histories had often been regarded as myth. Now researchers compared old accounts with mapped anomalies, noting surprising overlaps in some regions. While such stories do not replace scientific evidence, they offered a deeper human context and encouraged researchers to respect local knowledge as they probed the mystery. In academic circles, excitement tempered worry. Some researchers looked at the situation as a rare scientific opportunity. The layers exposed inside the holes represented untouched archives of environmental history. If sampled carefully, cores could reveal details about climate and ecology from thousands of years ago, offering new data on glacial retreats and the conditions that followed. Paleoclimate experts hope to use those records to refine models of how the region changed after the last ice age. The chance to access such pristine sequences of sediment attracted researchers from around the world. Colleagues from countries familiar with undersea anomalies flocked to see the data. Teams from places with submarine pit chains, rift zones, or hydrothermal systems compared notes. In those environments, the causes of similar features were often clear: plate movements, magma flows, or vent-driven chemistry. Lake Michigan posed a different problem because it sits on a continental interior that had been treated as geologically quiet for many generations. If active processes were at work there, the assumptions about continental stability might need revision. Researchers wondered whether slow, cryptic changes were common in other continental interiors, but had been overlooked because they were subtle and developed over long timescales. The more the team studied, the more they realized that old data mattered. Declassified military sonar records from the 1970s and 1980s, once dismissed as instrument quirks, contained echoes that on modern reanalysis sometimes lined up with current holes. The implication was sobering. The phenomenon might have existed at low intensity for decades, or possibly longer, and only recently reached a visible threshold. If that were the case, scientists had a longer temporal thread to follow and could search for slow drivers rather than expecting a single sudden cause. Monitoring operations ramped up. Buoys carrying sensors, deep water cables, and more drones fed a centralized data hub. Artificial intelligence tools helped sift through the torrents of telemetry, looking for subtle patterns humans might overlook. Analysts searched for links to seasonal pressure changes, distant earthquakes, or even lunar effects. Occasionally, they found small correlations, minor shifts in sublake pressure before some formations, but nothing consistent enough to build a predictive model. The holes appeared unpredictable in time and place, and that unpredictability magnified the difficulty of decision-making for managers and officials. Engineers ran worst-case simulations, even if the likelihood of catastrophe seemed low. They asked whether a large-scale slump or a chain reaction could generate localized waves or change currents enough to affect shoreline infrastructure. Those models helped municipalities plan contingencies, check the resilience of water intakes, and inspect underwater assets. Harbor authorities increased sonar patrols, and shipping companies were briefed to report strange returns. The response balanced caution with practicality. There was no call to evacuate or to halt commerce, but there was a clear push to watch closely and be ready to act if conditions changed. Environmental teams continued to track biological signs. To date, they noted little change in fish populations and plankton communities near the holes. Some scientists offered explanations. Perhaps the process was so gradual in parts that ecosystems adapted, or perhaps the holes opened where biological activity was already low. Still, researchers stressed that subtle impacts might show later, and long-term studies were necessary to catch slow-moving ecological shifts. Conservationists urged patience and careful monitoring before assuming the lakes were unaffected. Speculation sometimes outran evidence. On social media and fringe forums, people proposed outlandish scenarios, from secret drilling to alien machinery. Leading scientists dismissed such claims and urged attention to measured data and peer-reviewed study. At the same time, the presence of odd minerals and the unusual geometry of subterranean shafts kept some speculative doors ajar. Researchers reminded the public that science is a process of gathering data, testing hypotheses, and slowly narrowing possibilities. Extraordinary claims required extraordinary evidence, and so far the evidence pointed toward deep, poorly understood geological structures rather than anything paranormal. One profound consequence of the discovery was a change in how geologists thought about continental interiors. For a long time, the dominant view treated plates and boundaries as the places where dramatic change happened. Continental interiors were assumed to be mostly stable, relics of ancient mountain building and old glacial reshaping. If these holes reflect active, even if slow, processes deep beneath a lake in the middle of North America, scientists must consider whether similar features exist beneath other inland seas and lakes. The finding could prompt new surveys and fresh questions about how the crust behaves far from plate edges. As colder months neared, the research faced practical challenges. Ice cover would limit the use of drones and sonar, so teams rushed to gather baseline data. They stored core samples in controlled conditions and prepared for seasons when access would be limited. Many researchers accepted that the work would stretch over years. Patience and careful planning would be essential to unravel a problem of this scale. Throughout the investigation, the human element remained clear. Waterfront communities, indigenous groups, shipping interests, and scientists shared information in an unusual blend of local knowledge and high-tech analysis. Town halls allowed questions, and scientists learned to explain not only methods and findings, but also uncertainties. The phenomenon became a collective story, one that linked myths and manuscripts, sonar charts and sediment cores, and communities that have lived beside the lake for generations, with newcomers who study it from research vessels. Months into the effort, the holes continued to appear in new spots while offering fresh chances to study deep history. Each new core and sonar sweep added data, but also new questions. The official red alert stayed in place as a marker of seriousness and priority, less a signal of immediate danger, and more a call to devote resources and attention to something unprecedented. Researchers balanced concern with curiosity. They acknowledged potential risks and also recognized the rare opportunity to study untouched records from deep time. Lake Michigan's surface remained ordinary and beautiful, its waves crossing a water body relied upon by millions. Under that calm skin, the story was still unfolding. The holes were both a warning and an invitation. They reminded everyone that the planet holds secrets, even in places that feel known. Scientists continued to study, measure, and listen, hoping that patient work would transform the mystery into understanding and help communities prepare for whatever the lake might tell them next. For now, the lake carried on with its quiet power, and researchers kept watching the deep with a mixture of dread and wonder. The holes were not just empty spaces in the mud. They were windows into the long history of the region and into processes the science community had not fully anticipated. That balance of fear and discovery drove teams forward, committed to unraveling a puzzle that lay hidden under a familiar surface, and that might change how people thought about the ground beneath their feet for years to come. Researchers continued to collect data with care and patience. Each new core and sonar sweep added detail to a slow and complex story. Teams met often to compare notes and refine methods. Local people were kept informed through public talks and transparent updates. Scientists respected the voices of those who had lived by the lake for generations. The work required long hours and meticulous lab procedures. Students and early career researchers gained rare hands-on experience. The project became a training ground for future scientists. Funding agencies supported targeted experiments and long-term monitoring. That support allowed teams to buy better instruments and improve lab facilities. International experts advised on techniques used in other deep-water studies. They helped adapt tools to the unique environment of a large freshwater lake. Analysts looked for subtle signals across many datasets. They checked for links to distant seismic events and seasonal pressure changes. Sometimes small correlations emerged, but none were consistent enough to build a clear model. Models were used to explore how buried structures might behave over long time frames. Those simulations helped identify areas where additional caution was sensible. Engineers inspected critical infrastructure near mapped anomalies. Harbors and water intake systems received extra monitoring for any changes. Shipping companies were asked to report unusual sonar returns. Marine biologists followed plankton and fish populations for subtle shifts. At first, visible ecological impacts were minimal or absent. That observation was surprising and relieved many, but also raised new questions. One idea was that the process was episodic and slow enough for life to adapt. Another idea was that the most active areas coincided with spots of low biological activity. The research combined fieldwork with lab experiments to test these possibilities. Acoustic tests revealed unusual resonances in some cavities. These echoes suggested cavities or changes in material at depth. Electromagnetic surveys returned weak but noteworthy signals in certain zones. Those readings did not point to a single clear source, but they were not random either. Geochemists examined mineral grains and trace metals with precise instruments. Some isotopic signatures indicated exposure to high temperatures long ago. That result suggested ancient processes may have altered materials now exposed. Teams also reviewed cultural histories and oral accounts from indigenous communities. Those stories sometimes described features of the lake similar to the modern anomalies. Researchers treated such accounts as context rather than direct proof. Working together raised the quality of insights while honoring local history. The process of science unfolded slowly and deliberately. Data were published and peer-reviewed to allow independent validation. Transparent methods helped build trust and invited collaborative critique. Over time, previously dismissed sonar blips were re-examined and sometimes matched new findings. This longer view suggested the phenomenon might have been present at low levels for decades. That possibility shaped new questions about long-term drivers and cycles. Conclusions were cautious, but pointed toward deep, slow geological change. The discovery pushed scientists to rethink continental interior dynamics. In turn, new surveys were planned for other inland basins to see if similar features existed. Those surveys aimed to discover patterns rather than assume uniqueness. Meanwhile, the local public remained engaged and attentive. Community meetings helped explain the difference between immediate danger and long-term study. Officials stressed preparedness while avoiding unnecessary alarm. That balance helped maintain normal life along the shore, even as research pressed on. Teachers used the event to inspire student projects and classroom lessons. Young people learned about geology, conservation, and the scientific method. That educational benefit became one of the positive outcomes of a difficult mystery. Researchers hoped that patient study would reduce uncertainty and inform responses. They emphasized that understanding takes time and careful work. The red alert had focused attention and resources on the problem. It had also shown the value of rapid but measured scientific response. Looking ahead, the teams planned a phased approach of monitoring and testing. They identified priority sites for repeated scanning and sampling. They secured laboratory capacity for detailed isotopic and mineral analyses. They formed working groups to address specific questions such as acoustics, geochemistry, and hydrology. Those groups coordinated experiments to test competing hypotheses. Data sharing agreements allowed faster cross-checking and peer input. The collaborative model increased confidence in the emerging picture. As the months progressed, small patterns became clearer. Multiple lines of evidence suggested the holes related to buried structures affected by slow pressure or compositional shifts. That interpretation fit many observations, but not all, and researchers remained open to new data. They described the working model in papers and at scientific meetings to solicit feedback. Scientific humility remained a guiding principle as the community sought robust answers.